We end tonight with the clearest pictures yet of Neptune, the most distant planet in our solar system. Take a look. The striking infrared images were taken this summer by the James Webb Space Telescope.
The James Webb Space Telescope has once again delivered an astonishing cosmic revelation, this time focusing its powerful eyes on a scene of celestial violence, a massive collision in the outer solar system where something gigantic has just smashed into Neptune. The moment, captured in crisp infrared clarity, marks one of the most dramatic observations of planetary dynamics ever recorded. This isn't a blurry, ambiguous flash or a vague signal. Webb caught the unmistakable turbulence in Neptune's upper atmosphere, along with shockwaves of energy and particles rippling outward, the fingerprints of a recent and violent impact. Before we start, hit the like and subscribe buttons for more updates. The outer planets are no strangers to cosmic collisions, but for Neptune, these events are incredibly difficult to witness. At over 4 billion kilometers from Earth, Neptune's great distance and faint reflectivity make it a challenging target for most telescopes. But the James Webb Telescope, positioned at the L2 Lagrange point with its massive segmented mirror and powerful infrared sensors, has changed the rules of engagement. It sees through Neptune's hazy methane clouds, revealing layers of activity and movement invisible to Earthbound or even orbital telescopes like Hubble. That's what allowed it to detect the telltale signs of disruption in the planet's atmosphere, an unusually large and fast-expanding cloud formation at mid-latitudes, coupled with a stark rise in thermal output from the impact site. These features suggest a significant kinetic event, something that stirred up Neptune's deep and turbulent weather systems in a matter of hours. What exactly hit Neptune remains a matter of study, but Webb's high-resolution imagery and thermal data point to an object of substantial mass, possibly a rogue asteroid, an errant Kuiper Belt object, or even a minor icy moon destabilized by gravitational tugs from Neptune's chaotic neighborhood. Whatever it was, it had to be moving at tremendous velocity to breach the dense upper layers of Neptune's atmosphere and leave such a wide-ranging disturbance. The scale of the thermal bloom suggests the incoming body released as much energy as thousands of nuclear detonations upon entry, punching through the methane-rich envelope and generating shockwaves that Webb registered even hours after the incident. This event opens an entirely new chapter in our understanding of outer planet collisions. Unlike Jupiter, which has a long observational record of being struck, famously by the fragments of Comet Shoemaker-Levy 9 in 1994, Neptune has remained elusive in this regard. The planet's remoteness and lack of a solid surface make it challenging to determine long-term changes, but Webb's real-time monitoring has made it possible to analyze such a cataclysm as it unfolds. The data provides an unprecedented opportunity to peer into the complex atmospheric mechanics of Neptune and understand how such a planet absorbs, disperses, and recovers from an energetic impact. Infrared wavelengths have revealed the formation of massive vortices, resembling supercharged versions of Earth's hurricanes, which have been swirling around the point of impact. These systems span thousands of kilometers, moving heat and cloud material from the equator toward the poles. Some have speculated these temporary disturbances could evolve into semi-permanent atmospheric features, like the Great Dark Spot observed by Voyager 2 in 1989, a mysterious storm system that baffled scientists with its transient nature. Now, thanks to Webb, researchers can watch in detail as these formations grow, interact with Neptune's jet streams, and either dissipate or coalesce into something longer-lived. The implications of this discovery go beyond Neptune. Observing planetary impacts in real time allows astrophysicists to test long-held models of planetary evolution and collision frequency in the solar system. The outer planets, surrounded by rings of ice, rock, and countless small bodies, exist in a cosmic shooting gallery. Events like this confirm that even in the far reaches of the solar system, gravitational interactions remain dynamic and potentially violent. Neptune's mass and location make it a gravitational guardian of sorts, deflecting or capturing objects that might otherwise drift inward. But this recent impact shows that it's also a target, and the size of the impacting body suggests there may be far more large objects drifting through the Kuiper Belt than previously believed. This could have wide-ranging implications for planetary defense closer to home. If Neptune, a behemoth with a gravity field strong enough to tug small moons into orbit, can be struck by something this large, It raises concerns about the number of similarly sized bodies that might one day find themselves on a collision course with other planets, including Earth. Webb's detection of the object's heat trail long after the actual impact also offers hope for refining future early warning systems. If we can detect the thermal and atmospheric consequences of impacts from billions of kilometers away, we might also become better at spotting potential threats much earlier in their journey toward the inner solar system. Neptune's response to the impact has also highlighted some unexpected resilience and dynamism in its weather systems. Observations from Webb revealed rapid changes in cloud structure, with high-altitude methane clouds dissipating and reforming in different patterns than observed in prior months. Some scientists believe that the energy from the collision may have injected momentum into Neptune's already extreme weather systems, potentially altering wind speeds and jet stream alignments for weeks or even months. As Webb continues to monitor the planet, researchers will have the chance to track these shifts and possibly link them to long-term atmospheric changes. The planet's magnetic field also appears to have registered a temporary disturbance. Though Neptune's magnetic field is both offset and tilted, already making it one of the most complex in the solar system, Webb's instruments detected minor irregularities in the auroral patterns over Neptune's poles. These shifts might suggest that the impact, or the charged particles it created, briefly disrupted the delicate balance between Neptune's magnetic field and the solar wind. If confirmed, this would mark the first time a planetary impact was observed to affect a gas giant's magnetosphere directly, an exciting development that could reshape our models of planetary magnetism and external influence. One of the more captivating outcomes of this event is how it has reignited interest in Neptune as a subject of close study. The planet has long sat on the edge of our observational frontier, beautiful, mysterious, but remote and poorly understood compared to its siblings. Webb's clear and dynamic observations have changed that perception almost overnight. Neptune is no longer just the icy blue blur at the edge of our system, but a living, breathing world of weather, impact events, and dynamic change. There is also renewed excitement about the role Neptune plays in the solar system's architecture. It has long been theorized that Neptune's migration during the early history of the solar system helped shape the orbits of objects in the Kuiper Belt and even influence the formation of the other gas giants. Now, by witnessing a modern-day impact, scientists have a tangible demonstration of how this planet still interacts with its surroundings. The data might provide new insight into the distribution of mass in the outer solar system and inform searches for other, as yet undiscovered objects beyond Neptune's orbit. The James Webb Telescope's success in capturing this event also underscores the tremendous leap in observational capability that humanity has achieved. Before Webb, such an event might have gone unnoticed entirely, lost in the obscurity of deep space. Now, with its sensitive infrared eyes and high-resolution tracking, we can detect not only the aftermath of such collisions, but potentially their precursors, tracking fast-moving objects across the cold, dark expanse of the solar system and catching them in the act. It's an era of heightened vigilance and discovery, one that redefines what we consider observable. As more frames from the impact continue to be analyzed, scientists are beginning to reconstruct the trajectory and origin of the impactor. Preliminary orbital calculations suggest that it might have originated from the scattered disk, a region beyond the Kuiper Belt where icy bodies move in highly eccentric inclined orbits. If this is confirmed, it would bolster the theory that Neptune acts as a kind of gravitational gateway, occasionally drawing in ancient wayward objects from the system's farthest reaches. Each impact then becomes not just a moment of destruction but also a clue, an artifact from the solar system's chaotic past. The elemental signatures left by the collision are particularly intriguing. Webb's spectroscopic tools identified sudden surges in hydrogen cyanide, ethane, and acetylene, chemicals that can form under extreme pressure and temperature conditions. These molecules, briefly illuminated by the infrared afterglow, suggest that the object either carried exotic ices from the outer reaches or triggered chemical reactions deep within Neptune's cloud layers. Either way, the resulting data is a trove for chemists and planetary scientists who now have a rare look into reactions that would be impossible to simulate on Earth. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us, what are your thoughts on the massive collision with Neptune? What could it mean? We want to hear from you. Thank you for watching and see you next time.